this is section 1.7, the precise definition of a limit. And I will do a slight disclaimer about this section, which is just that it is probably one of the highest level sections that we talk about in all of Calculus 1, and yet it sits in chapter 1. So understand that it might take some time to get it, and that's totally reasonable and understandable. And also realize that it's not that it goes from here and just gets more difficult. This is, because we're talking about limits, it's the precise definition of limit, so it needs to be in chapter 1. But you will find that most other sections are just more straightforward or kind of less technical than this one. So we'll do the best we can. So in saying the precise definition of a limit, you might ask the question, what does it really mean to say that we have this limit that exists when x is approaching some value and then f of x is then approaching the limit? Like, what does that truly mean? So the real definition of a limit, the precise definition of a limit, is this. If for every real number epsilon greater than 0, there is a number delta greater than 0, such that if the absolute value of x minus a is greater than 0 and less than delta, then the absolute value of f of x minus L is less than epsilon. As long as that is true, we can say that the limit as x approaches a of f of x equals L. So again, for people that want this, this is epsilon, it's a Greek letter. This is a delta, this is a Greek letter as well. So this is often called epsilon delta limit, you know, the limit in terms of epsilon and delta. And then we will be doing some basic proofs, which are exciting, and we call those epsilon delta proofs. So big ideas here, just in terms of the notation. But really what it's just saying is, if we can get infinitely close in the x direction to some value, and that leads us to get infinitely close in the y direction to some value, then we have that limit that exists. So notice down here, this is what we're trying to approach. And what we're saying here is, as long as we have some delta, and again, delta is arbitrary. It can get, it's getting, you know, it can be really, really teeny. As long as we can be on either side of that x value that we're approaching, and as long as we do that, and then we get close to some value L with an epsilon of it, then we can say that the limit exists. So notice that essentially there's this like little box here, and that, you know, we have our, you know, value here that we see, but we are trying to show in a more precise, like technical way, that as we get infinitely close this way, we get infinitely close this way. We're using the idea of absolute value because epsilon and delta are both positive numbers, so we do need them to be, you know, using the idea of the absolute value, because we're in either direction from A, and we're in either direction from L. And so those differences here and here could be positive or negative. And so because we want to, you know, we'll use the absolute value to denote the distance, which is positive. Okay, so let's take a look at an example here. So for example, if we want, there we go. If we want the difference between a function and its limit to be less than 0.01, okay, so in either direction from the function, we want that limit to be between a difference of 0.1 on either side. We need some sort of delta such that the difference is less than 0.01 whenever you have a difference in your x values less than delta. So actually, we don't really need this thing here because I have it on the next slide. Pow! Okay, so we're going to take a look at an example, and hopefully over time that'll start to make more sense. So let's say we have a function f of x, and we want to approach 3. So you might look at this and be like, oh yeah, I see it. This is a line, you know, it's continuous. We have a hole at 3, so it's a line with a hole in it. But we're talking about what happens as we approach 3, and we're told that the limit is 5. So we're given that. So we're kind of like piecing ourselves together here. So for each value of epsilon greater than 0, determine a value delta greater than 0 such that when you look at the difference between the limit and the function, that will always be less than epsilon whenever in the x direction, that difference between x and 3, remember that's the x value you're approaching, is less than delta. And then we're given some epsilon. Okay, so what this is telling us is our epsilon is 1, and that's actually quite a big epsilon for the fact that we're trying to get infinitely close over time for the precise definition of a limit. But if epsilon is equal to 1, then the idea here is we want the difference between the function and this limit of 5 to be less than epsilon. So in this case, it's saying the difference, and that's positive and negative because it's the absolute value, needs to be less than 1. Okay, so if you wanted to kind of think of this, I'm going to come over here. This is an absolute value inequality. So remember that that means that we want the difference between the function and its limit to be less than 1, but greater than -1. Sorry for the tightness there. But that means that if we add 5, because we have -5 there, if I add 5 to each side, then that means we want the function to be less than 6 and greater than 4. So what that means is, notice our function here, this is our function f of x. We want to know, when is this function, for what x values is this function less than 6, greater than 4? So what we can do is we can kind of create that box like we saw in the picture on the last slide. Here is 6 and here is 4. So I'm going to draw lines at 6 and 4. And I'm going to think about, for what x values does this function stay greater than 4, less than 6? So thinking about that, you want to now think about the intersection. So where does these two lines that I've drawn, this y equals 6 and y equals 4, where do those lines hit with our function? So I'm looking for those intersections. So you can see that one of them is here. See if you can find the other one. Okay. So notice that's where we have the intersection of those two values. And then what we're paying attention to is what those x values are. So notice that we have at x equals 1 and x equals 5, we have the intersection. So here's the big idea. What this is telling us is that when epsilon is equal to 1, our function will always be between 4 and 6. And when it's always between 4 and 6, the x values for this function will always be between 1 and 5. So here we're thinking about delta. And delta is a distance from what value we're approaching, which in this case is 3, to whatever value it is, that's going to keep that function between 0 and 4. So that's how we're seeing the 1 and the 5. So notice that we're trying to approach 3. So that's right here. And then we're just thinking about, what is this distance here and what is this distance here? And the important thing to see there is it's the same on either side for us. So that's a distance of 2 on either side. So now we can say our job is to determine a value delta. So let delta equal 2. So as long as delta is equal to 2, then the distance between x and what we're trying to approach, 3, is always going, because as long as that's less than 2, then our function is going to be between 4 and 6. And that's what we were trying to find here. And again, these are pretty big delta and epsilons, but that's the idea. So what you can try to do now, because it's very, very similar, see if you can do epsilon equal to 0.5. Because what you should find is, you follow a similar pattern, and you should get something similar, just like it works out very similarly. So take a moment, see if you can do that, and then come back and see if you got it right. So I'm going to say the same thing because it's still the same function at the top. So f of x minus 5, so that's the function approaching its limit. We want that to be less than 0.5. That creates f of x, wonk, wonk, wonk. Okay, maybe I'll go over here. F of x minus 5, sorry about that, is less than 0.5 and greater than negative 0.5. That's going to give us f of x is less than. Now we're going to add that 5, so 5.5, and over here 4.5. So notice what it's doing is it's not quite 4 and 6, right? It's 4.5, 5.5. So we're getting closer to that limit with a smaller epsilon. So I have 5.5 here. So I'm going to do my line 5.5. I've got 4.5. So I'll do my line there. 4.5. I don't need to say that. And now what I'm doing, so once I have that, now what I'm trying to find is where that intersection is occurring. So where does this function, f of x, still the same function here, still f of x, where do we have those intersections? So we have, it looks like right here, and it looks like right here. Okay, and then we think about what those values are. So we see that that's 2 and that's 4. Remember that we're approaching 3. And so what we see is our delta is that distance that then guarantees that we're always going to be between 4.5 and 5.5, or what I should say is 0.5 from our limit in either direction. So notice that that distance is 1. So now we can say let delta equal 1. So as long as the distance between x, any x value, and our limit that we're approaching, 3, the value that we're approaching, as long as that distance is less than 1, our function will always be within 0.5 of our limit. Okay. What you should see, just to add on a little bit more, I was looking at my notes there to see, I was like, oh, I have something else written, that's right. So one thing that I do want you to see is that there's a pattern here. So I want you to notice the pattern between epsilon and delta. This occurs because this function is linear. So look at that, there we go. So when epsilon was 1, delta was 2. When epsilon was 0.5, delta was 1. So if you notice the pattern, and we've only done 2, but there is a pattern. So I'll write pattern. And for every epsilon that we can pick, you should notice we let delta equal. So notice 1 and 2, 0.5 and 1. Hopefully you see that our delta is just 2 times our epsilon in this case. And that would be true no matter what epsilon I pick. So if I picked epsilon being 0.25, what would delta be? 0.5. And again, this works because we have a linear function that has that constant slope. Okay, so now we're going to do a proof. And notice it's kind of a guided proof that what we're doing here is we are going to prove something using this idea of the precise definition. So we're going to prove that the limit as x approaches 3 of 2x minus 1 does in fact equal 5. Now you might say, well, I can just plug in 3, and 2 times 3 is 6, and minus 1 is 5, so I know that it's true. But that doesn't prove it. That's using the limit laws that we've learned that tell us that it is in fact 5. But this is more about like, why is it 5? So here are the steps that we need. So we're going to first start writing the inequalities we would need. And what you want to remember is that we want to be close. Every time we're close in the x direction, we want to be close in the y direction. So we're always going to have the absolute value of x minus, and then whatever the x is that we're approaching. So in this case, x minus 3. That's always going to be greater than 0. It's an absolute value, so it's going to be greater than 0. And we want it to be less than delta. And then we want, anytime that is true, that f of x minus our limit, which in this case is 5, to be less than epsilon. So absolute value again there. So the scratch work is done to decide what that delta is going to be. So we do some scratch work, we use some algebra, and we're trying to find a delta. And as opposed to the last two examples where we're like, okay, if epsilon this, delta is this, if epsilon is this, delta is this, we're trying to say what would it be at any point in time that will always guarantee what we need, which is that close, infinitely close this way is infinitely close this way, no matter what the values are. So we start with the scratch work. So we've got the 2x minus 1. So notice this is our f of x. This is f of x. This is the function here. That's what we have in the limit. So f of x. And we subtract our limit. So that's why you have this. And so all you want to do is say, we want this thing to be less than epsilon. So we start with that. Then we're going to simplify what we have in our absolute value. So we have this. So you can keep going with this if you want. You can see we can combine some like terms and we get this. Okay. And then what a really good thing to do now is, and what we really need to do is notice that we have a factoring situation. So notice, what can you factor out from that absolute value? And then of course, right here is where you should go, this is, even though you were dealing with f of x and the limit, now we have this thing that we've seen in the x direction. So that's kind of interesting and useful. And we want to remember that because we just have a 2 here, absolute value of 2 is 2, so we can actually bring that out so that we have this, and we have this. And then the most exciting thing is that now we can divide both sides by 2. The point of this, the point of all of this is to see that what we have here is the function, and it's in function notation, right? We're not being given some certain epsilon. We have a function, we're subtracting 5, and that is less than epsilon. And what we find out is that, so this is basically saying when that is less than epsilon, now that's telling us, just by doing some algebra manipulation, that the difference between x and 3 is less than epsilon over 2. So this tells us our choice for delta. It needs to be epsilon over 2. And what this is telling us, again, because we're dealing with the function and x, not being given epsilons, it's telling us that we will always, this pattern will always be the case, so that now we can prove this in the more technical capacity. So now here's the formal proof. Okay. This is what we write. Okay, so given epsilon greater than 0, whoa, that was weird. Epsilon greater than 0, we choose delta to be epsilon over 2. So this is what we just did from the scratch work. Delta is going to be epsilon over 2. Then what we know is that if the difference between x and what it's approaching is greater than 0 and less than delta, then, and notice what's happening here, we've got 2x minus 1 minus 5. So that's what we already had. So if we're close in the x direction, then in looking at our y direction here, the 2x minus 1, our function minus our limit, the absolute value of that, just we've already done this. So this is where the scratch work just comes back in. So notice I'm just doing what we just did. So I'm just working backwards here. So we just take that, we're just doing some algebra here. then here is the point where we get very exciting. So because of this fact right here, we know that the absolute value of x minus 3 is less than epsilon over 2. Now I can say that this thing is less than 2, because I just have a 2 there, so I have a 2 there. And then what the absolute value of x minus 3 is, which we know is epsilon over 2. And of course, 2 times epsilon over 2 is epsilon. So the whole point here is what we've proved is that as long as our x values are close together, the x value with the limit that we're approaching, which is 3, is less than delta, then we've got that our y values are less than epsilon. So the y values, the function and its limit, is less than epsilon. And that's the whole point of the precise definition of a limit, is that if we're close in the x direction, we have to prove that we're close in the y direction. And so we've done that. So now we can say, so if the absolute value of x minus 3 is less than delta, then the absolute value of f of x minus 5 is going to be less than epsilon. And by definition of a limit, we now have proven that to be so. So let's do one more. What you would, if you can, what you want to do right now is you want to pause and use what we just did to see if you can get the answer for this, because notice it's all very much the same. It's just a different function. We're approaching 4. For the function 4x minus 15, it's equal to 1. Again, you can plug it in and be like, yeah, it's equal to 1. We're trying to show that using the precise definition. So if you follow along the last one and see what you can do, that'll create a better learning experience for you, and then you can come back and watch me do it. That would be the way to go. Okay, so in this case, notice some different numbers here. Sorry, this is small for anybody. Okay, so now we're saying close in the x direction as x approaches 4. Are we close in the y direction as well? So now we've got our scratch work. You should hopefully over time start seeing this pattern. So at less than epsilon, we want that difference in the y direction to be less than epsilon. Notice a lot of the same stuff is happening here. Hopefully you see it, that when we divide by 4, we're going to have this. And this is where we're trying to get to. We're trying to use what we have, the difference in the y direction, to give us some values or teach us something about the x direction, which then will give us our delta. So notice when the function and 1, that's the limit, the difference between them is less than epsilon, the absolute value of x minus 4, the value of x with its limit, with its what we're approaching, the difference between those, the distance, is less than epsilon over 4. So that tells us what we need for delta, epsilon over 4. And the big idea, going back to the graphical representations that we saw early on in the second slide, is just what we're doing here. Like we saw that there was a pattern. This is what the pattern is. As long as delta is equal to epsilon over 4, then the difference between the function and its limit will always be less than epsilon. And so we don't need to choose epsilons because it's always going to be this case, this pattern. Okay, so now given epsilon greater than 0, we choose our delta to be epsilon over 4. So what this tells us is as long as the difference between x and 4 is less than delta, then, and then we just work our magic here, work backwards from what we've already seen, which is, that's the scratch work is just to figure out what you need. And then of course it just comes back, right? It helps you. So this is really the key step here. We do a few steps of algebra. Everything's equal. And then I take this fact that the absolute value of x minus 4 is less than epsilon over 4 to replace that x minus 4 with what it's less than. So, or yeah, it is less than 4 times epsilon over 4. So I'm just taking this 4, bringing it over here, but since this is less than this piece is true. And then of course, 4 times epsilon over 4 is just epsilon. So again, what we've shown is that if we're close in the x direction, here, then the y direction will be less than epsilon, precise definition of a limit. So that's what I'm just saying here. I guess I should just write it down. So x minus 4 is less than delta, then f of x minus 1 is less than epsilon. And that's by definition of a limit. We have our limit, and it is 1.